Learning Outcome 1-3. Determine memory, causality, stability, linearity, and time invariance given an input-output definition of a system. This video is for the subproperty time invariance. The definition of time invariance is a system is time invariant if, given any input x of t and output y of t, any time shift of the input x of t minus t naught results in an identical time shift of the output y of t minus t naught. What does this mean? Here we're looking to see that when you're running an experiment, it doesn't matter what time you start the experiment. It doesn't matter if you're in lab section 1 or lab section 3. It doesn't matter if you did your experiment in the morning. It doesn't matter if you did your lab experiment in the evening. So long as you're applying the same input to your system, you should be getting the same output returned. This is very useful in a practical sense. Time invariance together with linearity are two properties that we're going to assume are always satisfied for all of our systems in chapters 2 and forward. So let's take this definition and see how we apply it to a system. We have our input for our system and our output for our system. We can define inputs x1 and x2, just two different inputs, and they will produce, respectively, outputs y1 and y2. We want to see what happens when x2 is a time-shifted version of x1. Remember that for linearity, we said what happens when x3 is the sum of x1 and x2, or when x2 was a scaled version of x1. It's the same idea, that now we're looking at that y2 is going to be that same y1 shifted by the exact same amount. Let's work on an example. Y of t is 2x of t. Is this system time invariant? I want you to pause the video, go back to your notes what we did for linearity, and write the first two steps. They're going to be the same first two steps that you used for linearity in those proofs. Look at your notes, go back and review the video if you need to. It's really important you try to do these things without just letting this video play forward. Pause the video and don't continue until you have those two written out. I hope that these are the two steps that you wrote out. They're the same first two that you saw in linearity for both additivity and for scalability. What we're going to do now is the same thing as the third step or the next step that we came up with for linearity. In linearity, we said that x3 was x1 plus x2, or we said that x2 is equal to a scaled version, a times x1. Here we're looking at time invariance. We want to say that x2 is a time-shifted version of our x1. This will be our third step always. We're now going to take this and substitute it into our definition of our system 2. We're going to have algebra. Again, please use the square brackets to make sure that your notes are clear to me and clear to you. Next, we're going to take this first definition of our system and restate it. We want to see that if we were to shift this output, are we going to get the same thing that we had here for y2? So we're going to look at it time shifting, replace all of our t's with t minus t naught. That's going to shift this output. And we're going to say that y2 is that shifted version of our y1. Take this t replaced by t minus t naught. Take this t replaced by t minus t naught. And this is what y2 is equal to. We now need to say, is this value the same thing as when we shifted our input up here above? If this line matches this line, then we're good to go. And here they are. We can now put a check mark and say that for this system, time invariance is satisfied. And this is equivalent to saying this system is time invariant. Let's try another example. Y of t is t times x of t. We want to know, is this system time invariant? Again, I'd like you to pause the video and write the first two steps used to prove or disprove time invariance. I hope that these are the first two steps that you came up with. Now pause the video and write the step to shift the input. This is the same third step that we did for example 1. Once you've written that, then apply it to system number 2. This is the equation that you need in order to shift your input. And when we apply this into system number 2, we just make a substitution, and this is the output we wind up with. Now pause the video, restate the definition of the system for the first input, then write the step to shift the output. Once you've shifted that output, apply it to that first definition and see what you wind up with for the Y2 with this method. Restating of system number 1, we shift our output by replacing our t's with t minus t naught. Y2 is going to be the time-shifted version of Y1. So we take this Y1, everywhere there's a t, and now we got this extra t here. We plug those in. We now need to compare this definition of Y2 with this definition of Y2. What does Y2 look like when we shifted our input? What does Y2 look like when we shifted our output? Are these two the same? This time they are not, so we say time invariance is not satisfied. This is equivalent to saying the system is not time invariant, or saying the system is time variant. You got to be really careful here, because in one case we have a not, and the other one we do not have a not. So you got to be really, really clear not just to say yes or no as the output for this question.